This is Ken Rosever. We're going to talk about t-distributions. In another video, we talked about t-distributions and when you use them. I made this analysis, but the big idea, the main idea was if sigma is not known, then you use t. However, there's some caveats. If n is greater than or equal to 30 and sigma's not known, you can still get away with using z because of the central limit theorem. And if n is less than 30, you can only use t if the population is normally distributed. So that's what we talked about in another video. So population normally distributed. But what is a t-distribution? A t-distribution is a non-normal distribution. It's very similar to a normal distribution in that it's bell-shaped, it's symmetric about the mean, median, and mode are equal to 0 and are located at the center of the distribution, so they're centrally located, and the curve has a horizontal asymptote at y equals 0 and never touches the x-axis. Where it differs from the normal distribution, the standard normal distribution, is that its variance, and therefore its standard deviation, is greater than 1. So it's a little more spread out, or a lot more spread out, depending on the degrees of freedom. Okay, the t-distribution is actually not one curve, but a family of curves that's based on the concepts of degrees of freedom, which is related to the sample size, and I'll talk about that in a second. And as the sample size increases, the t-distribution approaches the standard normal distribution. In fact, when n is greater than or equal to 30, z, or a standard normal curve, is approximately equal to a t, which is a t-distribution. Okay, both this chart up here and this graphic are found on page 368 in your book. In fact, I would strongly recommend that you read pages 368 to 369 if you want a good understanding of what you're doing. If you just want to know how to do it and be kind of pragmatic, then this video will suffice, but I might not be able to get into all the nitty-gritty of why and how or whatever, I don't know. But I'm going to try to explain a little bit of the theory. Here's what I want you to see here. The reason I included this picture is because I just said a second ago that a t-distribution is not one curve like a standard normal. A standard normal curve is set. It's always this dark black curve that you see there. But a t-distribution depends on the degrees of freedom, and the degrees of freedom depend on your sample size. A way to understand degrees of freedom is, let's talk about tests. If you're computing a test average, and there's 6 tests in the class, so you have test A, test B, test C, test D, test E, and test F. Hopefully those weren't your grades. If I pick any 5, and the test average is known, let's say the average is 80, and I know this is a 81, this is a 62, this is a 45, this is a 93, and E isn't known, but F was a 87. Okay. You see how knowing this guy over here and knowing the other 5 determines E. E is determined already. So E is not free. It's not a free variable. These 5 variables are free, but E is not. In fact, if the sample size was 8 instead, then we would have 7 free variables, and once 7 are decided, the 8th one is already decided as well. So that's the concept of degrees of freedom. It's how many values are free to vary when the sample statistic is already decided, is already known. So for means, it is 1 less than the sample size. So that's pretty much what you need to know here. I don't know if I'm saying it as eloquently or as clearly as some other people might say it, but the degrees of freedom, at least for means, is n minus 1. Having said that, if you have a sample size of 9, your degrees of freedom is 8, and so you would have a curve. You see this one is the 5th curve. You would have the 8th curve. You can kind of think of the t-distribution as being a set of 30 curves. There's actually more than 30, but once you get up to 30, it's practically the same as the z-curve. But you can think of it as being like 30 unique curves that you pick from based on the sample size. If the sample size is 9, you use the 8th curve. If the sample size is 21, you use the 20th curve. If the sample size is 6, you use the 5th curve. And that's the distribution you use to compute probabilities. Okay, so it's not one curve, it's many curves, and the curve you're using depends on the sample size, which determines the degrees of freedom. Now, understanding that, we can then go into ALEKS and start doing some problems. So let me log in. So here's a t-distribution type problem. It says consider a t-distribution with 9 degrees of freedom. So when it says 9 degrees of freedom, we know the sample size was 10. And it wants us to compute the probability of a t-score that is greater than or equal to negative 1.20. So if you think of a t-distribution, it's still symmetric. It's kind of like a z or normal distribution, except it might be more spread out. But you can still use that basic bell-shaped curve because it's still a bell-shaped distribution. Remember, that is the first property here. It is still bell-shaped. So it's still pretty much the same picture. In the middle, you still have the mean, okay? And you still have, instead of z-scores on the bottom, now you have t-scores. Now this one is the 9th curve in that series or set of curves that I talked about. We want to compute the probability of a t-score that's greater than or equal to 1.20. So let's say that's over here, negative 1.20. And since we want greater, that would be shaded to the right. Now here's where the T button in ALEKS differs from the Z button calculator. The T button, you notice, instead of Z has a less than or equal to symbol, T has a greater than symbol. And you notice that the picture shades in the right side. Again, the picture shades in the right side, to the right of our cutoff value. So let's hit it. And you notice it has two things, because it's not one t curve, there's many t curves. So I need the right t distribution. I need the one with 9 degrees of freedom. So I put in a 9 there. And now I want it greater than negative 1.20. So that's easy. I can just type into the box. I don't have to use the complement rule or anything like that. I hit enter, and there is my answer. It is 0.8696. But they want it to 3 decimal places, so I'm going to call it 0.870 or just 0.87. So I'm done with that. Now the next one, it says consider a t-distribution with 29 degrees of freedom. Find the c value, the value of c, such that the probability from negative c to positive c encompasses 95% of the area. So going back to this, a little different problem, but I'm going to go like this. There's a c and a negative c, which leaves 2.5% on either side and 95% in the middle. And we want to discover what that c is. Now if this were a z, we just go z of alpha button, or the z with the little square, right? And for alpha, we type in this value right here. Well, it's no different for t. You still use t of alpha button. So let's find that in ALEKS and use it with 0.025 because that is the leftovers on the tails. So I'm going to hit this button right here, and you can see the picture. Alpha is the right tail there. So what I want in the right tail, I want 0.025, but of course every t distribution is different, so I got to select the appropriate one by indicating the degrees of freedom I'm working with. And having done that, my answer is 2.0452, or just 2.045 is sufficient. 2.045. And that's how you do these. That's our first video. I'm going to do another one. So that's it.